going to revise solutions chapter. Okay. Solutions. Solutions are homogeneous mixtures of two or more than two components. Homogeneous mixtures means all the components are uniformly distributed throughout the solution. Solvent is the component that is present in larger quantity in the solution. Solute is the component that is present in smaller quantities in the solution. A binary solution is composed of two components. Solutions may also be known as ternary or quaternary when it is made up of three or more components respectively. Solvents determine the physical state in which solution exists. Types of solutions. Solute, solvent, types of solution and examples. Solid solutions, liquid solutions and gaseous solutions. Solid, solid, solid in solid. All alloys like brass, bronze and alloy of copper and gold, etc. Liquid solid, liquid in solid. Amalgam of mercury with Na, CuSO4.5H2O, FeSO4.7H2O. Gas in solid. Solution of H2 in palladium. Dissolved gases in minerals. Liquid solutions. Solid, liquid, solid in liquid. Sugar solution, salt solution, I2 in CCl4. Liquid in liquid. Benzene in toluene, alcohol in water. Gas in liquid. CO2 in water, NH3 in water. Gaseous solutions. Solid in gas. Iodine vapors in air, camphor vapors in N2, liquid in gas, water vapors in air, HCl3 vapors in N2, gas in gas, air, O2 plus N2. Expressing concentration of solutions. Mass percentage, percentage weight upon weight. Mass of solute upon total mass of solution. Mass of solute into total mass of solution into 100. Amount of solute in grams present in 100 gram of solution. Effect of temperature, no effect. Mass by volume percent. Percentage W upon V. Mass of solute upon total volume of solution in ml into 100. Amount of solute in grams dissolved in 100 ml of solution. Changes with change in temperature because its volume is contained in this formula. Volume percentage, percentage V upon V. Volume of solute upon total volume of solution into 100. Volume of solute in ml dissolved in 100 ml of the solution. Changes with change in temperature. Strength, gram per liter or gram per dm cube. Mass of solute in grams upon volume of solutions in liter or per dm cube. Amount of solute in grams present in 1 liter or dm cube of solution. Changes with change in temperature. Parts per million ppm. Number of parts of solute upon total number of parts of all components of solution into 10 to the power 6. Number of parts of solute present in million 10 to the power 6 parts of solution. Temperature, no effect. Mole fraction, x1 equal to n1 upon n1 plus n2 or xa equal to na upon na plus nb. Ratio of number of moles of one component to the total number of moles of all the components. Temperature has no effect. Molarity, m. Moles of solute upon volume of solution in liter or decimeter cube. Number of moles of solute dissolved in 1 liter or 1 decimeter cube of solution. Changes with change in temperature. Molarity is temperature dependent. Molality. Moles of solute upon mass of solvent in kg. Number of moles of solute present in 1 kg of solvent. Temperature has no effect on molality. Solubility of substances is its mixture amount that can be dissolved in a specific amount of solvent at specified temperature. Factors affecting solubility of solid in liquid. Nature of solute and solvent. Polar solute dissolved in polar solvent and non-polar solutes in non-polar solvents like dissolved like. Effect of temperature. If the dissolution process is endothermic, delta H greater than 0, the solubility increases with increase in or rise in temperature. For endothermic reaction, you have to increase the temperature. And if dissolution process is exothermic, that is delta H is smaller than 0, the solubility decreases with rise in temperature. When the reaction is exothermic, what you have to do is to decrease the temperature. Okay. Effect of pressure. Pressure does not have any significant effect on solubility of solids in liquid, as these are highly incompressible. Factors affecting solubility of a gas in a liquid. Effect of pressure. Henry's law states that the partial pressure of a gas in a vapor phase is proportional to the mole fraction of the gas in the solution. Therefore, P equal to Kh into X, where Kh is the Henry's law's constant and is different for different gases at a particular temperature. Higher the value of Kh as at a given pressure, the lower is the solubility of gas in liquid. Since Kh is inversely proportional to the mole fraction, so when you will increase Kh, X or mole fraction will decrease, hence solubility will decrease. Effect of temperature. As dissolution is an exothermic process, then according to Le-Chatelier's principle, the solubility should decrease with increase in temperature. Dissolution is an exothermic process, so you have to decrease the temperature so that solubility can increase in cases of dissolution. Raoult's law. Raoult's law states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. P1 equal to P degree 1 x1 and P2 equal to P degree 2 x2, where P1 degree and P2 degree are vapor pressure of pure components 1 and 2 respectively at the same temperature. According to Dalton's law of partial pressure, P total equal to P1 plus P2, which is further equal to P degree 1 x1 plus P degree 2 x2, which can be further written as 1 minus x2 P degree 1 plus x2 P degree 2, which is further equal to P degree 1 plus P2 P degree 2 minus P degree 1 x2. If y1 and y2 are the mole fractions of the component 1 and 2 respectively in vapor phase, then P1 equal to y1 into P total and P2 equal to Pt into y2. So what you will do is y1 equal to P degree 1 x1 upon P total, y2 equal to P degree 2 x2 upon P total, and P total is P degree 1 x1 plus P degree 2 x2. Okay. Vapor pressure of solutions of solids in liquids. Vapor pressure of solution at a given temperature is lower than the vapor pressure of pure solvent at the same temperature. Solution is having lower vapor pressure than that of the pure solvent. Ideal and non-ideal solutions. Ideal solutions obey Raoult's law at all temperature and concentration. P1 equal to P degree 1 x1 and P2 equal to P degree 2 x2. Delta H mix is 0, delta V mix is 0, but delta S and delta G never equal to 0. They have given this question in earlier NEET exams. AB interaction is almost equal to AA and BB interactions. Example is N-hexane and N-toluene. Do not form azeotrophs. The ideal solutions are constant boiling mixtures. Non-ideal solutions do not obey Raoult's law at all temperature and concentration, and P1 not equal to P degree 1 x1 and P2 not equal to P degree 2 x2. Delta H mix not equal to 0, delta V mix not equal to 0. AB interactions not equal to AA and BB interactions. Non-ideal solutions forms azeotrophs. Non-ideal solutions show positive and negative deviations from Raoult's law. Solutions having positive deviations, AB interaction is smaller than AA and BB interaction, means that new solution which is formed between A and B is having weaker bonds than those of the AA and BB interactions. AB interaction is weaker than that of AA and BB interactions. Delta H mix greater than 0, delta B mix greater than 0. P initial greater than P degree 1 x1. For minimum boiling azeotrophs, positive deviation showing solutions show minimum boiling azeotrophs, higher vapor pressure. Okay. Examples: ethanol and acetone, carbon disulfide and acetone, methanol and water, cyclohexanol and cyclohexane. Ethanol containing solution shows positive deviation, and solutions showing negative deviation, AB or newer solution form is having strong bonds, that is AB bond is greater than AA or BB interactions. Delta H mix smaller than 0 and delta B mix is smaller than 0. P initial is smaller than P degree 1 x1. For maximum boiling azeotrophs, so there will be less vapor pressure. Examples are phenol and aniline, chloroform and acetone, chloroform and diethyl ether, chloroform and benzene, water and H2SO4, or water and HNO3, water or HCl. Okay. So in positive deviation there will be rise, but in negative deviation there is a fall. Okay. Now qualitative properties. Qualitative properties are the properties which depends on number of solute particles. Qualitative properties depend on number on solute particles, irrespective of their nature, relative to the total number of particles present in the solution. These are relative lowering of vapor pressure by Raoult's law. P degree 1 minus P1 upon P degree 1 equal to x2, which is further equal to n2 upon n1 plus n2. P degree 1 minus P1 upon P degree 1 equal to n2 upon n1, which you can write P degree 1 minus P1 upon P degree 1 equal to n2 upon n1, which you can write W2 upon m2 upon W1 upon m1. So it will give W2 upon m2 into m1 upon W2. Or you can write for dilute solution n2 smaller than n1, so we neglect n2 from the below ratio. Okay. Relative lowering of vapor pressure, P degree 1 minus P1 upon P degree 1 equal to n2 upon n1, or you can write P degree minus P degree S upon P degree S. Now, elevation of boiling point. Solutions have lower vapor pressures and hence higher boiling point than pure solvent. The increase in the boiling point delta Tb equal to Tb minus T degree B is known as elevation of boiling point. For dilute solution, delta Tb is directly proportional to molarity. Delta Tb equal to Kb into M. Kb into W2 upon M2 into 1000 upon W1. From here you can find the molar weight of the solute, molar mass of the solute, where M is the molarity of the solution and Kb is called boiling point elevation constant or molar elevation constant or ebullioscopic constant, having unit kg per mole. Definition of freezing point. The lowering of vapor pressure of a solution causes a lowering of the freezing point compared to that of the pure solvent. The lowering of the vapor pressure of solution causes a lowering of freezing point compared to that of the pure solvent. The decrease in freezing point delta Tf equal to T degree F minus Tf is known as depression in freezing point. For dilute solution, delta Tf directly proportional to molarity, or delta Tf equal to Kf into M, Kf into W2 upon M2 into 1000 upon W1. Here, from here you can find the molar mass of solute, where Kf is known as freezing point depression constant or molar depression constant or cryoscopic constant, having unit kg per mole. Osmosis and osmotic pressure. The net spontaneous flow of a solvent molecule from solvent to the solution or from a less concentrated solution to a more concentrated solution through a semi-permeable membrane is called osmosis. The minimum excess pressure that has to be applied on the solution to prevent the entry of solvent into the solution through the semi-permeable membrane is called the osmotic pressure. Pi equal to CRT. C equal to N. C here is just like molarity, so you can use N2 upon V into RT. Pi V equal to W2 upon M2 into RT. M2 equal to W2 RT upon pi V. Two solutions having same osmotic pressure at a given temperature are called isotonic solutions. If one solution is of lower osmotic pressure, it is called hypotonic with respect to the other concentrated solution. The more concentrated solution is said to be hypertonic with respect to the dilute solution. If pressure higher than the osmotic pressure is applied on the solution, the solvent will flow out from the solution into the pure solvent through the semi-permeable membrane, and the process is called reverse osmosis. It is used in distillation of seawater, desalination of seawater. For substances undergoing association or dissociation in solution, the molecular mass determined by studying any of the colligative properties is different from the theoretical expected value, and the substance is said to have abnormal molar mass. Van 't Hoff factor I is defined as the ratio of experimental value of the colligative property to the calculated value of the colligative properties. Van 't Hoff factor I equal to number after the reaction and number before the reactions. So experimental value upon calculated value, you can also say I equal to observed value of the colligative properties upon calculated value of the colligative properties. I equal to calculated molar mass upon observed molar mass. So molar mass is just reverse, that is I equal to before molar mass upon after molar mass. Okay, but number is just reverse, that is I equal to before number and after number. Sorry, after number upon before number. That is total number of molecules of particles after association or dissociation upon number of moles of particles before association and dissociation. For association I is smaller than 1 and for dissociation I greater than 1. So how you can learn it? Like this. When I am having one hand, then it is one particle, but after I dissociate it is becomes 2. So I equal to after number and by before number, so 2 upon 1. So I will be 2. Okay. Modified equations for colligative properties. P degree minus P degree 1 upon P degree 1 equal to I N2 upon N1. Delta TP equal to IKB into M. Delta TF equal to IKF into M, where delta TB equal to TB minus T degree B and delta TF equal to T degree F minus TF. Okay. Pi equal to I into N2 upon V into RT. Relation between Van 't Hoff factor and degree of dissociation. Alpha equal to I minus 1 upon N minus 1. Relation between Van 't Hoff factor and degree of association. Alpha equal to I minus 1 minus I upon 1 minus 1 upon N. 1 minus I upon 1 minus 1 upon N equal to alpha for association, and for dissociation alpha is equal to I minus 1 upon N minus 1. Okay, so this is all about this solution chapter. Focus on the positive and negative deviation. They ask questions from this and numerical parts like elevation in boiling point and depression in freezing point. Just it. All the best.